Welcome everyone, and welcome Jeroen to this first talk in the spring semester of the Computational Methods in Architecture lecture series, which is part of our MSc in Computational Methods in Architecture at the Welsh School of Architecture, Cardiff University. My name is Wasim Jabi. I'm a professor at the school, and I direct this MSc. And today I am very happy to welcome Jeroen van Lith, who's an architect and computer scientist. He holds an MSc in architecture from Delft University of Technology in the Netherlands, and an MSc in computer science from the University of Bristol, not far from where we are today. After having worked as an architect and artificial intelligence researcher, he founded PlanFinder, and that's how I got to know about his work through the software that he has created. PlanFinder is a software company which focuses on using machine learning to accelerate architectural design workflows. In the past, he taught at Delft University of Technology as a tutor in CAD and BIM. And in this talk, Jeroen will discuss ways in which PlanFinder uses machine learning. Some of the particularities of the application of machine learning within architectural design will be discussed, ranging from BIM data formats, repetition within documentation, and translation to widely used machine learning strategies. Welcome, Jeroen, and the floor is yours.
Thank you, Wasim. Thanks for being here. Let me just start sharing my screen.
Yeah, let me stop sharing, actually. Yep.
So, yeah, if everyone can see my screen, then I'll just start the presentation. So yeah, for the Welsh people under us, like I also copied or translated the title into Welsh, but I'm not going to pronounce it because I don't think I'll be very good at it. But welcome everyone. Really excited to be here. Really excited to talk about machine learning and how we at PlanFinder apply it in workflows for architectural design. Yeah, so first of all, hi, I'm Jeroen. Yeah, you can pronounce it like Jeroen, but over the years I've become very tolerant to other pronunciations as well. So yeah, you can call me whatever you want. I indeed have like an architecture background and a computer science background, and since 2019 I'm the founder of PlanFinder. So PlanFinder really is a software company. We're based in the Netherlands. And yeah, like Wasim already said, like we're really focused on accelerating existing architectural design workflows using machine learning. And that manifests itself mostly into plugins for Rhino, Revit, and Grasshopper. But we also do some consultancy work on the side. And I think what's interesting is we released the software last year. And we're now like, we now have clients all over the world. So it's really exciting to see that there's some adoption as well. The content of this talk, so we'll be mostly focusing on like machine learning in architecture. So not so much like a sales pitch of PlanFinder, but more like, you know, what's under the hood happening. And we focus on like the application of machine learning within the plugins of PlanFinder. So we start with the COVID-19 planner, which we did a few years ago when the crisis broke out. Then we'll talk about a small new plugin we're building, as well as PlanFinder, the main plugin of PlanFinder. And at the end, we'll dive into one of these workflows of PlanFinder a little bit deeper and to kind of, yeah, go really into depth a little bit more. To see what's really happening under the hood. And afterwards, there's time for questions, of course. So machine learning in architectural design. So yeah, just a refresher for everyone. I think it's pretty clear, but machine learning really is like a subset of algorithms within AI or artificial intelligence. There are all sorts of other algorithms within AI as well, but machine learning has become really popular over the last 10 years. And I think what's really important with machine learning, how it's different from these other algorithms, is that the logic which we try to achieve is really derived from data. So rather than, you know, there are also other ways in which you can derive logic, but with machine learning, it's really important that the algorithm is doing something with a data set. And you might think like, you know, especially I think as an architect, you might think like, when do I want to use machine learning and why do I need to use it? And I think it's interesting to think about, like, when I'm building a facade, for example, like when I was working as an architect, I was building a parametric facade, and you don't really use machine learning for that, right? Because you already know the logic from which you want to build a facade. So maybe you want to connect floors, and then you want to create beams, and then you want to, maybe from those beams, you want to create panels and so forth. So there's a way in your head in which you can formalize the logic, perhaps into a Grasshopper or Dynamo script. But sometimes it's also like you come towards a problem in which it's very difficult to formalize the logic. So for example, like if you have an image, which is basically just a list of pixels, a list of values, if you want to create an algorithm which classifies whether there's a hot dog in that image, yes or no, then it's very difficult to come up with rules, just like you did for the facade, to come up with rules which classify a hot dog in that image. And why is that? Well, because hot dogs tend to look different when they're being shot from a different angle. There are all sorts of different angles you can take. There are different types of hot dogs. And so this becomes like an extremely difficult task to formalize into a Grasshopper script or into a computer code, right? And so in those cases, it might be easier to let the computer learn it from examples and let the computer learn the logic rather than you trying to write down all the logic. So there are like multiple machine learning types. The three most popular ones are supervised learning. So that's really learning and mapping from some input to some output. But there's also other ways to use machine learning. We'll also cover during this lecture some of unsupervised learning, and that's really the idea of like obtaining some sort of structure from a data set. So you can think of something like clustering, where maybe you work at Netflix and you want to see certain patterns and behaviors of people watching certain series, and you want to cluster them in certain groups, so that like whenever I like a certain series, then it can also recommend me other types of series which other people in the same cluster also like. So it's really kind of trying to obtain some sort of logic or organization from a data set. And then there's reinforcement learning, which is another type of learning where it's really about like not making one decision, but making multiple decisions after each other in order to obtain a certain goal. And we'll mostly talk about supervised learning and unsupervised learning today. I think what's specifically interesting when we talk about like machine learning in architectural design is that we have to apply these things to architecture if we want to build software which accelerates some of the architectural design workflows. And I think the first thing which was for me very annoying is that the data we work with is kind of exotic. It's very different from your typical, let's say, bunch of text or a typical image. The data we work with is very different. Another thing which makes it a little bit more complicated is that we also represent buildings in different ways, right? Like we can represent a building as a hand sketch, or we can represent it as a Revit model. And there are all sorts of other ways as well. So there are many different ways in which we represent buildings. And I think what's also interesting is that it's like in architecture, I think architecture students know this better than me, but like it's unclear whether a design is good or bad. People have their own opinions. It's not as clear as, like, let's say I'm making a poker bot, a robot who plays poker, and I want to earn as much money. It's a very clear target. But in architecture design, there's not often or not always a clear target. Sometimes it's a little bit more unclear. And what also makes it a little bit more difficult within architecture is that we don't really have like large data sets available. We cannot just, for ChatGPT, they scrape the internet and get all the text. We cannot do that, sadly, because there are no good data sets available. And that also makes it a little bit more difficult to apply ML in architecture design. So yeah, let's focus a little bit on that data. So, often in architecture, we work with geometry. And then that's okay. Like there are some machine learning algorithms which you can apply directly on geometry. But then, like in architecture, we often not only work with one geometry, let's say one mesh or one polyline, but with collections of geometries, right? So all these things working together. So for example, you can see like a plan as a bunch of lines. And then what's specifically interesting for architecture as well is that like we often have like some semantic enrichment to that geometry, right? So it's not just a line, but it's actually a wall, or it's a window. And so we are dealing with this very niche data type. And I think what's regarding representations, what's interesting is that there are also lots of ways to represent a building, as mentioned earlier. So for example, there are different levels of detail, right? You can represent a wall with a single line, but you can also represent it by a very complex structure of like inner studs, insulation, finishes, and so forth. And that's very interesting as well, because machine learning, it's often easy to use machine learning whenever your data is somehow formatted in the same way, but that's not always the case for architecture. And also what's changing always is like the semantic enrichment. So like sometimes, we define a wall by just giving it the name a wall. Sometimes it's just implied because we look at a plan and, we see maybe a floor plan in CAD software, and nobody said it was a wall, but just by looking at it, we can see it's a wall. So it's implied, but that's also then a semantic, that's like a difference in semantic enrichment. And also like the way how we represent buildings in terms of geometry can vary, right? So like you can represent a building by lines, but also with meshes or with B-reps or whatever kind of geometry. So that makes it also very interesting. Like how can we try to find ways to represent these things in a kind of more common or in a way which is like more consistent. Yeah. So these are kind of the challenges which, at least for me, like really were present during the building of some applications for machine learning in architecture. Now we'll go through some of the applications PlanFinder built, and we go through a little bit of the ideas behind it. So for the COVID-19 planner, I don't know if you still remember it, but there was this big crisis going on a few years ago, and at PlanFinder we had this idea of like, it would be really interesting if if you have an office and you want to assign chairs in the office, but when you assign these chairs, you want to also keep that necessary distance, right? Distancing became very important. We cannot stay too close to each other, so we should keep some distance. And we saw this opportunity, like what if we can make a Grasshopper plugin which can automatically assign chairs within an office or in whichever kind of space in which you can assign these chairs automatically to chairs which you can use and chairs which you cannot use. So it's a plugin, it's available on Food for Rhino. And so it's really kind of aims to kind of maximize the amount of chairs you can use in a restaurant or in an office, but while keeping the distance. So all the chairs like have a minimum amount of distance between them. And so this looks a little bit like this, right? So like the algorithm starts to populate a set of unassigned chairs to ones which can be used and ones which cannot be used. So how does this work under the hood? So basically we have this empty set of points, right? We every chair we present as a point, and then what we do is we cluster them by proximity. So like we have this bunch of points, and then we say like, okay, we look for every point, we start growing with a certain distance, we start growing clusters, and then we come up in this case, in this example, with 2 clusters. And then what we did is we had this algorithm where we basically within every cluster we assign a point which becomes usable, so somebody can sit there. And then the next step is then to say like, okay, because this one is now usable, I'm now going to look into a certain radius to my neighboring points. And I'm going to assign these as unusable. And I'm going to repeat that process until there are no seats in my cluster left unassigned. And if you do that multiple times, then you can very quickly get to a good estimation of like chairs which you want to assign to be seated, and chairs which you cannot use. And this was kind of a quite easy way of using, in this case, the DB scan algorithm. So it's a density-based clustering algorithm to practically be used in an application for architectural design. All right, the next application of PlanFinder is Chonk. So Chonk is currently in private beta, so it's not released yet, but I think it's also interesting to talk about it from a machine learning perspective today. And it's really the idea of using unsupervised learning to structure data within architectural design. And that's because whenever we work with files in architectural design, like CAD files or BIM files, I think buildings often have a lot of repetition in them, but the repetition is not always captured. And why is that? Well, it's because sometimes it's annoying to use to work with blocks. Sometimes you get a file sent from somebody else who didn't use blocks or use families or whatever, and so you have got this kind of dumb file with all these geometries in them, but which are not clustered or sufficiently clustered. And so what if you can automatically find these blocks or find uniqueness within the file? And then you can maybe reduce the file size. You can increase the consistency. You can query counts more easily, and you can also, for example, when you're creating when you're fabricating something as well, you can look at what is the unique part of this geometry. And so if we look at buildings, then you can also see there's a lot of repetition, right? Even when you compare to Sagrada Familia, you can see these symmetries in there, there's so much repetition in it. But also typical floor plans, they often have lots of repetition in it. So that was really interesting for me. It's almost thinking about these things can be generated from a Grasshopper script, maybe the floor plan on the right could be generated from a Grasshopper script. But what if you can from a floor plan generate a Grasshopper script? So it's really kind of finding that finding the logic from the plan rather than generating it. And so it's really the other way around. And so what happens when you can actually start doing that? So what we do is we look basically at shape descriptors of the geometries. So we, whenever you have a file in CAD or BIM software, we look at, we go through the geometries, and we try to find a way to describe these geometries to basically define their uniqueness. So how we do that is we, in this example, we have polylines, and we get the centroid or the center or the average of the points in a polyline, and we calculate the distances between the average and the corner points of the polyline, and then we create a vector of all these distances, and that vector then becomes an identifier of that geometry, right? So you can then start looking at other polylines in your file, and you can you can compare them. And so if you know that they're the same, then you can actually start maybe replacing them with a block. And the cool thing as well is that these descriptors, they are translation, but also rotation, reflection, invariant. So that means that if the polyline is rotated somewhere else or translated or mirrored, it doesn't really matter, because you can still identify it because the distances stay the same. And so that's basically the core idea for Chonk, is to kind of use these shape descriptors, these identifiers, to then perform operations on them. And on the left, you can see how these shape descriptors can be used for singular geometries, but we can also start looking into clusters of geometries, where we cluster geometries by, for example, proximity, because that's often often in CAD or BIM, things which are close to each other also belong to each other, or have some relationship to each other. So what you can then also do is then create like composite descriptors of multiple geometries. And so you can basically use those as well to start looking for repetitions, not only in singular geometries, but also in multiple geometries. And so if you have the technique, we can also, of course, extend that to not only polylines, but also to blocks and to points and to meshes and so forth. So if you have these things, then suddenly, you know, if we have all these unique identifiers, and we can also make like identifiers of clusters, then we can maybe become much more powerful. And we will now like show you some of the features of Chonk. So one is, for example, like block replacement. So like if I here select the four polygons, then the algorithm can look into the whole file and look at whether there are similar composite clusters of these 4 polygons. And then when it actually sees them, then it can actually replace them with a block. And so you very easily replace a file which is maybe, you know, quite heavy because this chair has been or this dining table is being copied for 1,000 times. Then you can very quickly replace it with a block, and then suddenly you've got a parametric block, so you can change it and it will update the other ones automatically. So it's a really easy way of basically going from a dumb file to a more clever file. But what you can also do is you can select the unique the geometries, right? So I've got here a wall. I want to know for fabrication purposes, perhaps, what are the unique geometries within this file. So again, like we're using that similar or that algorithm which I showed you before, where we create this descriptor, and then we just go through all the geometries in the selection, and then we look at the unique ones, and then we only show the unique ones. What you can also do is select same, right? So rather than replacing a block, we can select similars. So for example, I selected this this table on the left, and it will look through the file and see like whether there are other composites of these shape descriptors in the file, and then you can do whatever you want with them, right? You can delete them, or you can replace them with something else. But it's again like using that same logic of basically using the composite descriptor to find other geometries in the file. And then there's also like the other block functionality, which basically suggests blocks according to some proximity. So we'll literally like go through the file. It will, based on proximity, make all these candidates for all these composite clusters, and it will look at repetition within these composite clusters within your file, and then can automatically suggest things which occur very often in the file and automatically replace them without you having to assign a certain block. So whenever you don't know which block you want to replace, you can still use other block, and it will try to automatically suggest blocks for you. And it will do that according to that proximity. So let me just show you that again. So you have to basically assign a certain proximity, and then PlanFinder will, or Chonk in this case, like will look at like descriptors in the neighborhood with a certain proximity, let's say 2 meters in this case, and then it will start to make candidates, right? And from all those candidates, it will then look at like what's the most occurring one, and from there on, it will start to suggest blocks for you. So those are really the applications for Chonk. This is right now in private beta, so it's not released yet, but I thought it was interesting to show to not only use like supervised learning, but also unsupervised learning, and to really kind of start thinking about like shape descriptors and using them to cluster things within your CAD or BIM files. So now PlanFinder, the main plugin of PlanFinder. PlanFinder really is a software which is basically doing things to accelerate the design of residential units within CAD and BIM software, in this case Revit, Rhino, and Grasshopper. Under the hood, they all use the same logic. It's just there's a small connection to Revit, Rhino, and Grasshopper. And there are 3 functionalities. So the first one is fit, which basically tries to fit an existing plan into a new design. Then there is furnish, which automatically furnishes plans which are empty or unfurnished. And then there's generate, which tries to generate plans from an empty plan, basically tries to fill it with walls and afterwards also furnish it. So this is a small demo of the fit functionality. So somebody's working in this case in Rhino, and PlanFinder will go through the database of floor plans of PlanFinder, and it will look for nearest neighbors in this case. So we'll look for like shapes which are similar to the one of the input. So in this case, a rectangle. So it's a from machine learning perspective, not super interesting algorithm. Perhaps it's just looking at like, you know, I've got a database of shapes which look like this, and then I've got an input, and then I'm just going to look like how far is the input from all these shapes in the database, and then it will return the best ones. So like it doesn't really manipulate the floor plans that much. So it's like it scales them a little bit, it rotates them, reflects them, translates them to make better fits, but that's it. So it's not really changing floor plans drastically. It's only transforming them in a limited way to make the fits a little bit better. Maybe it's also interesting to show, like in this example, you can see that like the input shape was slightly jagged, and so, or slightly not perfectly rectangular, and so it will not perfectly fit that, or the plan, the library will not perfectly fit the input. So it's like an example of like also the limitations of this algorithm. But because often in residential, you know, we often work with quite simple forms, we still think it's an interesting application, because often, you know, we do work with simple forms, or you can tweak the geometry afterwards to still make it work. And it works with all sorts of shapes, so also with L shapes, or whatever shape you would like to. And so how does this work under the hood? So it's really like we've got an input. Let's say on the left we've got this rectangle, and then on the top, in the green top, we've got all these plans in our database with all sorts of different shapes. And then it will basically try to really look at like how far is that input rectangle from all these other shapes in the database. And then it will calculate that distance, and according to that distance, it will return then the best plans which have the smallest distance, and then that will be then presented in the UI. The second functionality is then the furnish functionality. So you have an empty plan, you have to assign the outer walls, the facade, the interior walls, and the entrance, and then it will generate this furniture layout for you, which is also kind of interactive, right? So you can change doors or change the function of a certain room, and it will also generate like multiple furniture options per room. So like whenever you click on a room, it will generate, or it will pick another generated option. And then there's also UI where you can change the wall widths and so forth. So how does this work under the hood? So we start with an empty plan, right? And then we use convolutional neural networks to classify each room. We're actually moving that towards graph neural networks and do cycle classification, but right now it's basically a convolutional neural network for every room. It will go through the room and its surroundings, and it will then classify which function a room has. And then we've got like all the rooms assigned with a certain room function. And then from then we have another CNN or convolutional neural network, which tries to predict where doors go for every room. So we'll look at like, okay, in which room am I right now? In which room do I want to go? And it will make proposals for the best locations of these rooms. And then if we have the room functions and we've got the doors for every room, then we can start doing furniture placement. So we've got algorithms which often like 1D convolutional neural networks, which then place the furniture around the polygon of the room. That's also like an example which we'll go into deeper at the end of the presentation. And then at the end, you end up with a proposed furniture layout, including room functions and doors for that unfurnished floor plan. So it's really kind of breaking it down into these separate steps to make it more modular and to train models specifically for that task to come up with these solutions. Then the last functionality of PlanFinder is generate. So it's basically the same as furnish, but it will also generate the walls. So it will first predict the room counts for a certain plan. Then it has the room counts. Then it will predict where the walls go, and then it's the same thing as furnish, where you then start furnishing it. And like it's, I think, specifically useful for like more unusual plans where like fit is not going to work because this, there will never be a plan like this in the database of PlanFinder. So then it's more useful to use generate and try to find whether generate comes up with a solution. And it also generates multiple options, which are guaranteed to be geometrically different from each other. So you always know, like, okay, it generates up to 8 variants. And that like whenever it's generating something that is guaranteed to be different from the others. And we do that with the diffusion models. So if we look at the whole workflow, it's very similar to the furnish one. It's just that we have like a wall generation step in between it as well. And diffusion models really are what's also behind the popular post on Midjourney or DALL-E or Stable Diffusion. So it's like these image generators, which basically denoise an image. So you start with noise and then you start to gradually denoise it, and you guide it with some sort of intention of what you want it to generate. And then you can generate an image. The only thing which we change with regard to the diffusion process, or like in comparison to more traditional image generators, is that we don't really generate images. We generate, like, in the end, geometry. So we have to deal with that, right? So rather than generating continuous values for every pixel, we actually classify in the end like pixels into their entities which are required for the geometry generation. So we tweak the algorithm a little bit at the end to say, like, hey, we're not interested in what the specific continuous value of pixel is, but actually we want to have a class of the pixel. So we tweak it a little bit. And I think what's also interesting is like these the traditional convolutional neural networks, they often behave differently when you rotate an image or when you reflect an image. And so what we do under the hood is we basically rotate and reflect the image of the floor plan, so that we also actually leverage that to generate diversity in the plans. And thereby we're able to generate 8 variants in this case. So we basically leverage the fact that the CNNs behave differently when you rotate an image or reflect an image, and we use that to our advantage to generate multiple options. Then we also do some small validation of, is the generated plan actually a good plan, yes or no? Sometimes it generates a little bit ridiculous plans, and then we don't want to show that to the user. But after that, it's very similar to the furnish functionality, where we then furnish that anti-plan with the furniture, and we use the same procedure for that, and then we present it to the user as well. So I thought it was interesting to now go a little bit deeper into one of the workflows at PlanFinder, where we can really kind of show you hopefully a little bit of like how to work with BIM data as direct as possible. Maybe not use images or any other translation of your data, but to really be as close to the data as possible. And we do that with our furnishing functionality. So I thought it was interesting if we go a little bit deeper into that to kind of get you an idea of how we do that and inspire you hopefully a little bit. This actually, we also did this a few months ago at the Design and Modeling Symposium in Berlin. But it's really the idea of like, if I have an empty bedroom, I want to place a bed there, but how to decide what the best location is. So this is something you could maybe do in Grasshopper as well. But you have to write a lot of if statements, and it's never going to be perfect, and it's not going to be very scalable to all sorts of other cultures, for example. So it's an interesting machine learning problem, right? We've got this empty room, and we want to place the bed somewhere. Where do we place it? How do we represent this? So if we look at I just grabbed some images from the data from the internet, to look at like existing floor plans of bedrooms. And what you can see is that like often the bed is like perpendicular to the facade. So it's like standing like maybe a meter or half a meter away from the facade. But there are also exceptions, right? So the one on the image on the left shows that the plan is actually not perpendicular, or the bed is not perpendicular to the facade, but it's actually on the opposite side, right? And so we already know that like if we would come up with an algorithm which just place it on the perpendicular side, that's not going to work. So we have to, it's probably better to let it be learned, right? And that's exactly what we do at PlanFinder as well. So we use this particular strategy as well at PlanFinder to generate these furniture layouts. So yeah, how can we decide what the best location is? So I think first it would be interesting to think about like how can we represent this problem into a machine interpretable or interpretable problem for a machine. So we have to translate this problem into a bunch of numbers, and ideally also the data we work with has always the same size. So that's often works very well for machine learning when the data has like a similar size, and you don't have like data points which where there's lots of variety in size. So maybe what we can do is we can take some assumptions. So we can assume, for example, that the room can always be represented by a polygon, and the polygon is basically just a closed polyline. And we can also assume for now, we make it a little bit easier for ourselves, but we can also assume that the bed will always be placed on that polygon, so always on the outer edge of or on the edge of the room. Of course there are exceptions, right? Like if you have a very expensive bedroom, sometimes beds are not placed on the wall of the room, but actually like freely, for example, or they're standing freely. But we discard this for now to make it a little bit more simpler representation to make something which we can work easily with. And this is, by the way, also a very rare case, right? So we can safely disregard that for now. So like, how can we represent this problem then a little bit better for computers to understand? So on the right, there is like a diagram of like an example room. If we would have a data set like an example room, how we could represent it. And what you can see is like there are the outer walls, right? That's the polygon. Then we've got some special cases. For example, if we've got a door somewhere, an entrance, we've got a bed somewhere, and maybe there's also a facade on this room. And so what we will be doing is like basically we have the default representation of the room, which is the polygon, and then we insert special points or points of interest into that polygon. So we make this polygon a little bit, we add some extra points to that polygon. And in this case, what we do is we add a point for the door, and we add a point for the bed. So these are the things we're very much interested in, because we think that the door or the distances between the bed and the other points actually are very important for the machine to learn something from. And then we start enriching every point of the polygon basically with some data, right? So not only the geometry, because we're not only interested in geometry, but also the semantic enrichment. So we also look for every point. Is it on a facade, yes or no? And is it a door, yes or no? So then we end up with basically a vector for every point of 4 numbers, where we have the relative x location, relative y location, whether it is on a facade or not. So it can be a yes or no, or in computer terms, a 0 or 1. Oh, sorry, a 1 or 0. And then, you know, what you can see is already like this polygon is basically a loop, right? So it's basically an array, which is a circular array. So it's basically the ends attach to each other again. And that's then the data we can, in which we can represent this particular problem. It's of course a little bit abstracted, but that's okay for now. And then what kind of learning strategy do we want to use? Like, there are many ways in which we could start learning from this. But in this case, for PlanFinder, it's interesting to use a binary classifier. And we're going to have like a very simple strategy in which we have a data set of bedrooms with obviously the right location, because you know, all these beds are placed in a certain position in a room. So we label that those instances as true. But what we then also do is we start to randomly place the bed somewhere else in the room, and we label that as false. So basically taking the assumption that like if we randomly place it somewhere else than the original location, that's going to be not as good as a location as the true location. And so the idea is that like the binary classifier will learn what the good locations are, but also at the same time like what the bad locations are, right? And like in this example here, you can see on the left, this looks pretty plausible, like looks like a good floor plan. And on the right, like, yeah, it would be a real shame if you would have to put the bed, or often that's a real shame to put the bed on the facade, right? Because you cannot look outside, for example. So it's not something you would like. But the strategy right now is that the machine learning algorithm can automatically starts to distinguish like what is a good thing, because the good things are always very similar to each other, and the bad things, they're just always different, right? So they're always a little bit strange. And so we'll start to distinguish these two things. By the way, for the real nerds under us, you can also represent it in other ways, such as a regression problem, but we'll not do that for now, because we want to also potentially create multiple options, multiple design options. So how are we creating a data set from this? So what we want to do is create a data set with equally sized input data and output data. But of course, it can be a problem whenever like the polygon is has a lot of points in it. Then we want to find a way to still create like an equally sized data set from these polygons. And so what we can do is actually we can hook the polygon with an offset point count from the bed. So as you can see here, the bed is located here. And what we basically do is we say, okay, we look at the neighboring beds to the right and to the left with a certain offset, so with a certain count. So in this case, 3. So we take the 3 points on the right in this case and on the left, and we get all these vectors from all these points. And now and then we join all these vectors together into a table. And now we created basically a table which is always the same. And so we can apply this strategy now to any kind of room, because what we can just do is offset it. So we hook the polygon from 2 sides, we get all the points, and then we just create a table. And now we've created a strategy in which we can always use this with whatever kind of polygon, right? It doesn't really matter anymore. And we can also change the offset, right? So we can make it 2 or we can make it 5. But I think if we make the offset too large, then we probably have a lot of duplicate data. So we don't want to do that. So let's keep it for 3 for now. But that's also something you can play with when you would have to build this yourself. But anyway, we've created a strategy from which we then now have like a singular array of all these points, right? So it's basically a list of points. It's a 1D signal. And we have a label, right? So for every example, we have this true example, in this case on the right, but we also created this negative example or this bad example, and that would then have a label 0. And then for the learning model, because we're working with 1D data, it's very interesting to use like a 1D convolutional neural network, and that's a specific type of neural network which really is can learn well on data which has a 1D one-dimensional characteristic. And this really has like a 1D characteristics, because we're really interested in like, what are my neighbors? How far am I from the facade? How far am I from the maybe from the door? And so this works really well for 1D signals. And so what we can then do is apply a simple 1D convolutional neural network to the problem. And then we end up at the end with a single node, which indicates whether it's a bed or a no bed. And so now we've kind of have all the components together to build that. Yeah, a PlanFinder, we already built it, so we can now immediately show it. And so at the end, like, yeah, what we want to end up with is basically a model which can predict a bed for a given location, right? And we can basically prompt it or ask it like, how likely is it that the bed will be placed in that location? Yes or no, right? And so we can now start trying to put the bed on different locations in the room, because we don't know for a future instance, right? So we put it on different locations in the room, and we just ask the model, hey, how well do you think this is, or how good of a location do you think this is? Is this a true bed or a false bed? And it will return as a number between 0 and 1. And if it's very close to 1, it will probably be a good location. And if it's very close to 0, will be a bad location. And so what the cool thing now is that we can also make like not only one, we cannot predict this for one location, but we can basically start dividing the polygon into multiple points, and we can ask the model for all these different points how good of a location that is. And so what happens is that you can not only like generate one solution, but you can generate multiple options for where you want to place the bed. And I think that's like coming back to what we were talking about earlier, about like that there's no single truth in architecture design often, like there are many different opinions. I think it's also interesting that, like, you know, if we work on machine learning models to predict certain things, like in this case, very simple example of like placing a bed in a room, I still think it's interesting to create like multiple options, so that like it's still like you create a more kind of flexible model from which then the user can still is able to, you know, pick something rather than having one definitive answer, because that will never be perfect for everyone. And then, of course, this is not really the machine learning part anymore, but then, of course, for PlanFinder, we also have a UI, which then a user can click through these options. So here you can see like how that works in practice with PlanFinder. So it's basically you're doing that furnish thing, right? And it will generate these bed positions for every room. And I think what's interesting in this example as well is that like you can see that this bed is placed not on the perpendicular wall, but because the room is so wide, it actually like the best location for this bed, the model thought was actually on the back wall, which I think also makes sense. But you can also click through other options. So there was this other option. The second best option is still this option. So for some reason, it still thinks that that's the second best option. And then the third best option is a bed, which is also on that kind of back wall, but then a little bit closer to the door. So it's like a slightly different location. So it's basically now we have a flexible model from which we can then present that to the user, and we can present these different options to the user. So that's really like a way of using machine learning into your own project. Of course, I skipped over a lot of things, but like I think the ideas are very much there, and implementation you can always look for on Stack Overflow as well. But I think it's really interesting to apply machine learning as direct as possible to the problems we're facing in the AEC industry. And I think in the example, I really hope to show like that we can really use the direct properties of our BIM models in a machine learning model. And we don't really need to translate it to anything else. We can really apply models directly on our BIM models. So yeah, hopefully was that a little bit clear. Hopefully I didn't talk too fast, and I hope there are some questions, so I'm happy to answer them.
Thank you, Jeroen. That was really, really interesting, fascinating work. Just for our attendees, just a reminder, if you'd like to ask questions, please go ahead and put them in the Q&A section. I know there are few already populating there, so I'll give you just a couple of minutes to collect your thoughts and add questions to that. And I will start with a couple of questions just to give you that opportunity.
Yeah.
I guess, I mean, I'm just going to ask more kind of general questions. First of all, can you describe a little bit your journey? Because as you know, this is our audience, mainly the core audience is my students from the MSc Computational Methods in Architecture. So you are somebody who has studied for an MSc in Architecture, an MSc in Computer Science, and then launched a career that started a little bit in academia and then went and became an entrepreneur and a startup and did your own company. Can you describe a little bit that journey and just give them a little bit of an insight of possibilities and challenges as they, because some of them may pursue that.
Yeah, so I think it started for me by working as an architect, that I saw that, like, I think the business model of architecture practices is that you work from project to project. And so architecture firms are not really, or often not really, incentivized to let people really work on like things which expand above the normal project. And so I was always working on like things to automate, but then found that like I needed to work on a different project and I couldn't really, fully implement it or fully focus on it. So for me, that was kind of like a starting frustration that I thought, like, I have to, if I really want to focus more on automation or on these tools, then I probably need to change my career a little bit. And so that's how I kind of started this idea of like, okay, maybe I want to start programming. And then like I did some tutorials online, but I could never really focus really well on like really learning it. And so, it worked for me to do like a master degree in computer science, but I understand that like you can also learn things online very well. And so like I started with a kind of quite traditional computer science degree online, but kind of quite quickly realized that machine learning was really the interesting part within computer science, but that was not really being taught so much at the university. So that was then completely like online, just watching YouTube tutorials. So, and also I think like in a field which is changing so much, it's kind of, you really need to be on YouTube and on Twitter and all these things to and to really find out yourself as well, because it is relatively new. It's still relatively new, especially in AEC. And it's really, I think you really have to just start building it yourself, and you'll come up with your own problems, hopefully, and from there on you can start building, I guess.
Great. My second question is about the software itself and the methodology itself. Can you comment on how generalizable it is? What kind of work would need, for example, to change the building typology that you are working with? Let's say we're going to move into commercial buildings or hospitals or hotels. Can you give us an idea about do we need to train a new data set? Do we need to change the UI in major ways?
Yes. So yeah, the way I think we design buildings is different per typology of building. So like when I want to lay out like an office floor, I maybe have some sort of procedural algorithm in which I can generate like office desks or chairs or whatever. But residential, it really requires to, you cannot really capture that logic in any kind of procedure. So I would say like PlanFinder is extendable to kind of units or small problems from which you can then have a lot of examples, and then you start learning some sort of strategy. But it's difficult. It's different from a more kind of procedural perspective, from which also sometimes you make a layout. So for example, like if you have a car park, for example, you would never use, or you probably not use machine learning to generate a car park, because there are clear rules of how to generate the positions of the parking locations. But for residential and for maybe hotels or for Starbucks interiors, like then it's not so clear what the rules are. And so then when it's not so clear what the rules are, then it's often better to use a machine learning approach. Yeah,
as you said at the start of the talk. Thank you. So I think we have 6 questions. So I'm going to start going through them. The first one is from one of my students, Michelle. She asks, do you use graphs to train your convolutional neural network? Because I know you mentioned graph machine learning, which we are also interested in and we've done some work on. So do you use graphs to train your convolutional neural network? If so, how do you make the jump from graph to geometry to visualize the plan?
Yeah, so very good question. You can represent a plan as a certain type of graph. So we actually do represent, we actually started moving from convolutional networks to graph neural networks. And what you can do, for example, with graph neural networks is cycle classification. So like if you see a plan as a certain type of graph, and then you can also see like you can see the corner points of the walls as nodes, and you can see the walls as connections. And so you have a graph, right? And then the rooms are just like a cycle within that graph. Sure. And then you can start to do cycle classification within a graph neural network. So that's a strategy in which we also try to, again, like really directly on the geometry do machine learning rather than translate it to a raster, which we do right now, which is slightly inefficient.
For sure. Yeah. Second question from Artem. How did you make a library to train your models?
Yeah, so we work with architecture firms. Some of them say we cannot give our plans. It's very difficult because of IP. Other ones say, yeah, here you have 100 plans. So we have that, and then we also have our own ways to extend or enrich the data set. So what we do, and I think that's maybe a little bit too much to talk about right now, but I can explain it maybe in a very short way. Like we again use these graphs of these plans, and then if they're very similar to each other, the assumption is that you can also interpolate between them. Yeah. And so that's like an interesting way of basically extending the data set artificially. I think I put it on YouTube a few years ago, but you can basically, if plans look very similar to each other, you can assume that all the plans in between or the interpolation between the two is also an okay plan. And that then that works very well for machine learning, because then you can use much more data than your usual training set.
Yeah, we did in one of the MSC's dissertations, we did a similar procedure to kind of increase the number of sets, which is, let's say if you recognize a hinge, let's say an L-shaped plan, you can take one wing and start rotating it in different ways, and you can assume that the plan will still be workable, and that's a way to increase the number of test cases.
Yeah, what we did is we basically created a graph from the entrance of the plan, and then we just go counterclockwise. You go around the polygon and you start to build a graph. And if you do that always in the same way, then you end up with like graphs which are always described in the same way. And so you can then start to cluster them relatively easily.
Yeah, absolutely. Question from Amit. How do you search the floor plan database? Is it scale, rotation, invariant? And there's another question. It says to expand furniture placement into other positions in the room, not near the walls, would a grid work well?
Sorry, I couldn't really understand the last question. Can you repeat it?
So to expand furniture placement into other positions in the room, not near a wall, would a grid work well? So like
Yeah,
if
exactly.
you're in the living room and you are putting couches and carpets in the middle, would you use it?
Yeah, you could totally use that. So you could use like we use like a 1D example in the 1D convolutional neural net in the example, but you can also see it as a 2D problem, right? Like it's just a way of like, you know, for example, for placing a bed, it really makes sense that because it's so often on the wall that you represent it then as the polygon as a 1D signal, and you can represent it with a 1D convolutional network. That's very efficient. 2D is already like much more inefficient, so that's why we don't use 2D neural nets for that. And with regard to fitting, so the fitting really works according to like the shape of the input polygon and also the entrance, and then it will basically extend like the data set with also their reflections and their rotations and also some translations to try to kind of fit the input geometry as best as possible. So in that regard, like it does not only like look at how the plan is in the database right now, but it also looks at like ways of like, what if I would rotate it 90 degrees or 180 degrees, I would flip it. Would it then be a better fit, yes or no? And we also scale the plans a little bit whenever the user wants to make even better fits.
Fantastic. The next question is from one of my students, Nikila Wilson. She asks, what is the output of PlanFinder in Revit, drawings, or families? How do you interact? Okay.
Yeah, so it's both. So it's basically like the furniture elements. Often they are represented by a point-based family, but also like if you have a kitchen, it's maybe a polyline-based family, and then we have walls and rooms and so forth.
Great, thank you. Next question from Sam Gregson. He says, thank you. Question, could you expand on why you chose a diffusion model over, say, a GAN model? And could your generate strategy be used for building layouts on sites, do you think?
The last question I couldn't hear again.
Could your generate strategy be used for building layouts on sites? So almost like a test fit.
Yeah. I think that could be definitely possible as well. It's just the same strategy, but then maybe first trying to generate some sort of building plot, and then our footprint, and then from there on you start to do other things. So I think it's the same logic can be used. Why I don't use GANs? GANs are very difficult to train. That's the most important reason. Like they're very difficult to train. I've tried them very often, but they didn't really come up with good solutions. And I feel like there are some other interesting problems with GANs as well. But like to basically create these discrete entities at the last moment was more difficult as well to train. So let me see, are there other? Yeah, and also like I think like just empirically, GANs are not so relevant anymore. The diffusion models really work much better with regard to image generation. So it's like, I don't have the means to make like really good comparisons, but if I see that DALL-E is working really well, then I'm like, okay, I'm gonna try this now, and I'm not gonna be bothered by GANs anymore. I've tried them. It was very difficult, didn't really work too well. So yeah, I moved on.
Thank you. A second question from Michelle. Is there a specific logic to follow when fitting your plan within a polygon? Do you think it can be developed and applied to fit a plan into an irregular or organic shape? And is this something you are working on?
Yeah, so like the plans in the PlanFinder's database are pretty boring. So from a database perspective, they have pretty boring shapes. So like polygons of L shapes, rectangles, maybe sometimes a little bit different shapes, but they're very boring. But the input shape can be any kind of shape. So it can be even a curved shape is possible. So you can have any kind of shape. And what it really tries to do is it tries to look at it's a very specific algorithm, but it's basically like intersection over union. So it like tries to kind of make a Venn diagram of the plan in the input and the plan in the database, and then it looks like, okay, what is the intersection? So where do I overlap? But also
the question from Abdurrahman Al-Jahadali, he asks, do you think that drafting or drawing plans is no longer an architect's task?
Well, I mean, PlanFinder is not perfect, so it's definitely an architect's task. No, but I think, yeah, it is. I mean, of course, like AI will play a very big future, just like any other industry, right? Like, just like any other industry. And I think what's interesting is that these, especially like the fusion models, but also these language models, they also tend to show like real creativity. So that was always a thing where people would say like, yeah, creativity is really the last thing which AI will automate. Well, it's not the case anymore, right? Like AI can also be very creative. So like any other industry, like AI will just play a very big part in how we will work in the future. But I think like in the end, like humans are right now still very much on the drawing board and just using these tools to accelerate their work, but also become better architects, hopefully.
Great, thank you so much. Thank you everyone for attending. Let me just show you the where you can get this video later on. So I'm going to just share my screen.
Cool. I'll stop sharing mine.
Let's see here and this one. So we have a series of talks. We're building up kind of a database of talks. We're obviously new at this, but this is the URL. It's a playlist on my YouTube channel, and this is the QR code. If you would like to scan it with your phone, you can get there. There's already 3 talks by Malcolm McCullough, Matthias Del Campo, and Brian Johnson. And this talk will be added to that, and obviously future talks. Jeroen, thank you very much for your talk today. It was really, really insightful and very relevant, especially to the kinds of stuff that we are teaching here at the MSc Computational Methods and Architecture. So thanks again.
Cool. I really enjoyed it. Thanks for having me.
Thanks. See you
All
soon.
right. See you.
Bye.
Ciao.